In 2009, Joel Pett published this cartoon. We are at a climate summit, and a middle-aged white man, and it's always a middle-aged white man, stands up and interrupts the speaker and says, "What if climate change is a big hoax and we created a better world for nothing?" And then the speaker points at all the other benefits of greenhouse gas emission reduction. I'm going to investigate the merits of this claim. I'm going to talk about the ancillary benefits or the secondary benefits of greenhouse gas emission reduction. The argument I'm going to make is fairly mathematical. Let's assume that we have two things we care about. We have two criterion emissions, G and A, where G stands for greenhouse gases and A stands for air pollution. And we're going to measure these as emission reductions rather than as emissions. The benefits of emission reduction is alpha A plus chi G. So this is how much air pollution we avoid, and this is how much we care about that. This is how much climate change we avoid, and this is how much we care about that. Emission controls are for greenhouse gases and S for air pollution affect both of our problems. So if we reduce emissions by R, or if we make an effort for greenhouse gas emission reduction of R, then we reduce greenhouse gases by rho R, but we also reduce air pollution by the amount tau R. Similarly, if we go after air pollution, if we make an effort to reduce air pollution, then we reduce air pollution by our effort times a coefficient, so sigma S, but we also affect greenhouse gases by the amount pi S. Costs of emission reduction is the sum of the effort for controlling air pollution and the effort for controlling climate change, and they are simple quadratic forms, so half times lambda r squared and half times kappa s squared. So that is the entire model. We can take these equations and plug them into here, and then we get this expression that we can rework as a function of s and r, and that we have here. So we copy these two equations to the next slide. We have benefits, we have costs, so we can do a cost-benefit analysis by equating the marginal cost to the marginal benefits. The marginal benefits, dB dr, that is why we express this as a function of r, is alpha tau plus chi rho. The marginal costs is the first partial derivative of this thing here. This does not depend on r. Here we have a nice 1/2, so that cancels against the 2. So what we have here is a lambda r. Bring this to the other side of the equation, and the optimal emission reduction, the optimal greenhouse gas emission reduction, is chi rho over lambda plus alpha tau over lambda. Now this makes perfect intuitive sense. Chi is how much we care about climate change. Rho is how much our actions reduce greenhouse gases. So the higher any of these two numbers, the more we want to do about climate change. And then lambda is the unit cost of emission reduction. So the more expensive it is to reduce emissions, the less we want to do. So this makes perfect sense. This term also makes perfect sense. Alpha is how much we care about air pollution. Tau is how much our greenhouse gas emission reduction action affects air pollution. So if tau is 0, if we can reduce greenhouse gases without affecting air pollution, then this term vanishes. Again, we have to normalize this with the unit cost of emission reduction. So if tau is 0, then this effect disappears. Let's look at this graphically. So what we have here in the brown line is the marginal cost of emission reduction. We should set that equal to the marginal benefit that is shown here in the green line, and this is essentially this term here is this point. And then this point here, alpha tau over lambda, is this point here. This is what we would do about our secondary benefit. Now, this thing, and this purple line, vanishes if tau is 0. And if tau is positive, we want to work harder on our greenhouse gas emission reduction, because if tau is positive, if we reduce greenhouse gases, we also reduce we also reduce air pollution. And one example of this is if we take a coal-fired power plant and we replace it with a gas-fired power plant. That reduces CO2 emissions, but coal burns much dirtier than gas. Coal also emits a lot of sulfur, a lot of nitrogen, a lot of particulates. Gas essentially burns fairly clean and goes to CO2 and water, and that's it. So if you switch from coal to gas, you reduce greenhouse gas emissions, carbon dioxide emissions, and you also reduce air pollution. However, if you switch from petrol to diesel cars, then you reduce CO2 emissions because you get much more oomph out of a liter of diesel than out of a liter of petrol. And that means that you have fewer CO2 emissions per kilometer driven. So this reduces carbon dioxide emissions, but diesel burns much dirtier than petrol. In particular, you emit a lot more particulate matter. So in this case, your tau is negative. And then the sum total is, well, if these are the marginal secondary benefits, and if they're positive, if your tau is positive, then you want to work harder on your greenhouse gas emission control because there is this additional secondary benefit. But if your tau is negative, if reducing CO2 emissions makes air pollution worse, then you need to subtract this and you go from this line to this line, and you want to work less hard on greenhouse gas emission reduction. Now, final point, if climate change is a hoax, and that was my starting point, that means that your your chi is zero. That is, there is no climate change, or there is no concern about climate change. Then this term vanishes, but this one remains. You may still want to reduce greenhouse gas emissions because of the air pollution benefits that it brings, provided that your tau is positive. If your tau is negative, then you actually want to emit more greenhouse gases, right? Now, let's set the problem up symmetrically, so the same reasoning holds for your optimal emission control for air pollutants. And this is the expression here. This is how much you care about air pollution. This is how much your air pollution action affects air pollution. This is how much you care about climate change. And this is how much your air pollution policy affects climate change. And again, the question, do you want to work harder or less hard on air pollution, depends on the sign of pi. And again, if you switch from coal to gas, then you emit less air pollution and also less CO2 emissions. So in that case, your pi is positive. But there's a different way of reducing your sulfur emissions from your coal-fired power plants, and that is to put scrubbers on smokestacks. And that takes away a lot of your sulfur emissions, but it also uses a lot of energy. About a third of the energy, about a third of the electricity that you generate in your power plant gets diverted to the scrubber and actually takes away, it's more like a quarter, about a quarter of the energy of the electricity that you generate in your power plant is diverted to your scrubber, and that means in order to produce to deliver the same amount of electricity to the net, you need to burn a quarter more coal. So your CO2 emissions go up, and in that case your pi is negative. To sum up the first part, if greenhouse gas emission reduction helps solving other problems, such as air pollution or energy security or whatever problem takes your fancy, then we should do more of it. But that is, of course, contingent on the assumption that you help improve these problems, and that is not necessarily true. It can also make such problems worse. At the same time, what we should keep in mind, going back to our scrubbers, other problems do not necessarily justify a lot of greenhouse gas emission reduction, as the best way of solving air pollution is to go after air pollution, and go after air pollution directly rather than through a roundabout way via greenhouse gas emission reduction. So that suggests that the tau The tau here is smallest, and the pi here is also smallest. I will now introduce a complication into the model. The equations are as they were, except for the red parts. Particularly, I'm going to introduce an interaction between the two policies, and I'm going to make the secondary benefits less than linear. So the benefits are as they were. Greenhouse gases are also as they were, not affected, but in our air pollution or the emission reduction for air pollution, I'm going to introduce this particular cross term. So it still depends on S and R, but now it also depends via parameter psi on R times S. And the best way of thinking about this is given in this equation here, where your air pollution reduction effort depends on your air pollution reduction depends on the effort for air pollution reduction and a parameter sigma, as it was. It also still depends on your greenhouse gas emission reduction effort, but the greater S, the smaller this effect becomes. So previously it was just tau, but now for larger S we take away part of this benefit. And the way of thinking about this is that yes, greenhouse gas emission reduction reduces air pollution, but if you also have an air pollution policy that takes away most of air pollution, then there isn't much for greenhouse gas emission reduction to take away anymore, because most of it is gone. And that is how you should read this particular change in the model. Costs of emission reduction are still the same. The benefits, rework them again, and the new introduction are the interaction term alpha psi r. Copy the two equations to the next slide and do a cost-benefit analysis by equating marginal benefits to marginal costs. Marginal costs haven't changed here, lambda r. Marginal benefits are the old expression, but now this thing comes on top, so we have to take the first partial derivative of this thing to r, so that becomes psi s, and of course we need to multiply that by alpha, because that's how much we care about air pollution. We can solve this equation for r, and what we find is the expression that we had previously, minus alpha psi s over lambda. And this is again intuitive. Lambda is the cost of greenhouse gas emission reduction, so we should also normalize, always normalize with that. Alpha is how much we care about air pollution, so that pops up there. Subtracting something, psi s, essentially s is how much air pollution we have reduced, and then psi is how much of that effort takes away the benefit of reducing the air pollution benefit, the secondary benefit of reducing greenhouse gases. And graphically, that looks something as follows. I'm going to assume that the tau here is positive, because we talked about it before. So this is the marginal primary benefit, and this is the marginal primary benefit plus the secondary benefit. So this thing here is chi rho. This thing here is alpha tau. The marginal primary benefit plus of the difference between the two is alpha tau, is the marginal primary benefit plus the secondary benefit, assuming that there is no climate and there is no air pollution policy. But then if there is air pollution policy, if you've already taken away part of your concern and therefore also taken away part of your secondary benefit, you go from this line to this line, and your optimal emission reduction goes from this point to this point. It falls, right? So that is how you should read this graph. There is one problem with this derivation, that r depends on s and s depends on r. So this is not a complete solution. And what you can do is work this out, because this is two linear equations in two variables, and you find this particular expression here. So your optimal r prime is this expression, and this is just the old expression, right? Previously with alpha tau plus chi rho over lambda. Now we multiply the two, both above and below the bar, we multiply by kappa, so that just drops out. So this is the old expression here. All these things depend on psi. So if your psi is 0, then the red terms all just disappear. And what we have here is the lowering of the bar, and this essentially reduces the slope. This is still the cost. So that looks something as follows. So this is the marginal primary benefit. This is the primary benefit plus the secondary benefit, assuming that there is no air pollution policy. But if there's air pollution policy, you reduce the primary benefit, the secondary benefit, so you go from the dark green line to the lighter green line. But then because of the interactions between the policy, you reduce the slope of the brown curve into this curve, and then you push it slightly further out. So the reasoning here is that you worry about climate change, so you reduce greenhouse gas emissions. Then you discover that you also reduce your air pollution, so you want to work harder. But then you discover that there's also air pollution policy, so you work less hard. The air pollution policy does the same thing. It essentially says, okay, I'm going to reduce my air pollution, and I'm also going to cut greenhouse gas emissions, so I'm going to work a little bit harder there. But then you discover that they start working harder, so I should start working less hard, and that interaction, and that means that you actually move slightly to the right again, and the marginal cost curve tilts downward, tilts this way. So, the first three conclusions you have seen already. If greenhouse gas emission reduction helps solve other problems, then we should do more of it. It can also make these problems worse, and then you should do less about climate change. Other problems do not necessarily justify a lot of greenhouse gas emission reduction, as greenhouse gas emission reduction would be a clumsy way to solve other problems. And that's the conclusion of the final part. Secondary benefits shrink with policies aimed at these problems. The harder you work at solving your air pollution, the lower the secondary benefit of reducing air pollution through greenhouse gas emission reduction.